Hello, everybody. I'm gonna go over homework number 3 solutions. So the solutions are already posted, but I did want to go through the problems individually and show you how I solved these problems. So let's jump right straight to them. Problem number 1: suppose that you arrive at a single ATM to find 5 other customers in the bank, one being served and the other 4 waiting in line. You join the end of the line. So there's an ATM. There's an ATM. There's one person already being served, and then there's, think of this is the front of the line. There's 4 other people waiting. 1, 2, 3, 4. Okay, you join the end of the lines. So this person would be me. This is you at the end of the line. You join the end of the line. If the service times are all exponential with rate mu, what is the expected amount of time you will spend in the bank? Okay, or at the ATM line. Okay, so let's see. This is a pretty simple problem. I think of it different ways. The next event in the system is the first departure. Right? So that first person, the first person who's already at the ATM, they're going to depart. This expected time, okay, is going to be call this x1. The expected value of x1, because it's exponential, is simply 1 over mu1. If we want to look at the second departure, okay, this time span, call this x2, that expected value is also 1 over mu. So it probably not mu1, just mu. Okay, so and then the third departure, fourth departure, fifth departure, etc. Right. So I am the 1, 2, 3, 4, 5, 6 person there. So it's going to be the expected total time for myself. If I call that t, it's going to be the expected value of x1 plus x2 plus x3 plus x4 x5 plus x6. Okay. Then I can break these down to expected value of x1 plus expected value of x2 plus the expected value of x3 all the way to the expected value of x6. And each one of these are just 1 over mu. Okay, so then my answer then ends up being 6 over mu. Okay, this is a straightforward problem. So it's a simple asking what is the expected value for you when you're at the end of the line. It's simply 6 over mu. Problem number 2. Consider the bank of qual example that we did in class. There are 2 clerks serving customers in a bank. One clerk can only serve 1 customer at a time. Suppose Peter enters an empty line but finds Brian and Stewie being served by the clerks. Peter will be served when one of the 2 clerks become available. Show that if each clerk serves a customer at an exponential rate lambda I, then the probability that Peter is not last is the following. Okay, it gives you the expression. So let's again draw the diagram. I want to call this clerk 1, this clerk 2. I have Brian and Stewie, so Brian is over here, Stewie's over here, and Peter can go to either line, whichever becomes free. So I want to know the probability. I want to show that the probability is not last is given by this expression. Okay, so let's kind of think about how we're going to approach this problem. Okay, you can visualize 2 cases in which the Peter won't be the last person to leave the bank. Okay, the first scenario is, say Brian is the first one to leave, okay, and then Peter ends up going into clerk 1 where Brian was. Okay, so you can imagine Peter's over here. Then once Peter gets to clerk 1, Peter finishes prior to Stewie. So that would be the first case. Okay, so I'm going to solve out that scenario first, and then I'll solve out the other scenario. The first scenario, we got to assume this is the probability. Okay, this is the probability that Brian finishes before Stewie. Okay, that's the first event that has to happen, and right afterwards, probability that Peter finishes before Stewie, given that Brian has finished before Stewie. Okay. This portion, the first part, probably that Brian finishes before Stewie. That's just the figuring out if one exponential is less than the other one. So that's going to be lambda 1 over lambda 1 plus lambda 2. Okay. So given then that Brian has already left, and we're left with Peter's going to Peter's going to go to clerk 1, then right at that instant again, it's like the reset button, right? So at that point again, the probability then that Peter is finished before Stewie then is again lambda over lambda 1 plus lambda 2. So we get lambda 1 over lambda 1 plus lambda 2, the entire quantity squared. The other case is Stewie finishes prior to Brian, and then Peter will take Stewie's place at clerk 2, and then Peter finishes before Brian. So the second case is the probability that Stewie finishes for Brian, and the probability that Peter finishes before Brian, given that Stewie finished before Brian. Okay, so the probability that Stewie finishes before Brian is simply lambda 2 over lambda 1 plus lambda 2. Again, you're comparing two exponential distributions. The probability that one's smaller than the other one is given by this nice property. Given that Stew's the first one to leave, then you're left with Brian and Peter. Again, then who's going to finish before first? We want to know the probability that Peter finishes before Brian. That's again lambda 2 over lambda 1 plus lambda 2. So the whole quantity becomes lambda 2 over lambda 1 plus lambda 2, entire quantity square. So at the end then, probability that Peter is not last is simply the first scenario plus the second scenario. So it's going to be lambda 1 over lambda 1 plus lambda 2 square plus lambda 2 over lambda 1 plus lambda 2, entire quantity squared. Okay, that's how we take care of show that the probability that Peter's not last is simply breaking down these two situations. Let's take a look at problem number 3. We're going to let x1 and x2 be independent exponential random variables, each having a rate mu. Okay, so I'm going to let x1 be an exponential random variable with parameter mu. x2 is also an exponential parameter with parameter u. X1 is the minimum between x1 and x2, or x parentheses subscript parentheses 1, and x2 subscript parentheses 2 is the maximum of x1 and x2. Okay, so kind of look at a timeline here. 0, you can think of x1 as this first event, and then x2, it's actually this entire thing. That's x2 being the maximum event. Okay, so first part A, I want to find the expected value of x1. That's like saying the expected value of the minimum of x1 and x2. Okay, so given that something is the minimum of two exponential functions, we know this is just going to be 1 over the sum of the lambdas or the mu's, because when you take the minimum exponential functions, it starts behaving like an exponential function on its own with simply all of the lambdas combined. This will be 1 over mu plus mu. Okay, so you get 1 over 2 mu. Part B, I want the variance of x1. Okay, so how do I get the variance? So the nice property of an exponential distribution is that the expected value of an exponential function is just 1 over lambda. The variance of x, simply 1 over lambda, the whole quantity squared. Okay, so if I want the variance of the minimum of x1, x2, it's simply going to be 1 over 2 mu. That was my expected value. The entire quantity squared, so we get 1 over 4 mu squared. Okay, that's how we show the maximum minimum. And now let's go on to part C, which is a little bit more complex. So part C, we want the expected value. We want the expected value of the maximum of these two, x1 and x2. There's many ways to solve this. I can just integrate and get an answer directly. I can use some of the derivations I showed in class, but I'm going to try a different approach here. Okay, so I'm going to first relabel this little stretch here as A. Okay, so if I rewrite this, this is simply the expected value of x1 plus A. Okay, so if I want to find the expected value of x2, it's like getting the expected value of x1 plus A. And this is where we could actually exploit the memorist property, right? Okay, as soon as the first event occurs right here, okay, we're memoryless, right? It's memoryless, so that the expected time for whatever's remaining, it's again back to 0, so it's 1 over mu again, right? Because both x1 and x2 have parameter mu, this problem is a lot simpler. Okay, so as soon as that first event, either it's x1 or x2, whichever it happens, right at that moment, then the expected time for whatever's remaining is again 1 over mu again, right? So we can rewrite this as, we already filled this, you can think of this as expected value of x1 plus expected value of A. Okay, we already have this portion, right, from part A. So I know that's going to be 1 over 2 mu. Okay, right after that happens though, the expected value of A is whichever's left over. It could be x1 or x2 that's left over. They're both mu, so the expected time then is just 1 over mu. And that's my answer. Okay, so if you exploit the memorist property, this problem becomes very, very simple. And it's a lot easier than trying to integrate or do something fancy. This is using simply the properties of memorist property, using the memorist property to get the answer. Okay. Now let's move on to part D. Okay, stick with the red color. It's the variance of x2. So it's the variance of the maximum between x1 and x2. Here again, I'm gonna, if we want to use this property here, okay, then it's pretty simple. Except though, we can't really just take this 3 over 2 mu and square it, right? Because it's really composed of two random variables. So what we're really doing is the variance of x1 plus a. Okay. The common property of a variance is that if they're independent variables, variance of x and y is simply going to be the variance of x plus the variance of y if they're independent, right? So the same thing over here. This is going to be the variance of x1 plus the variance of a, okay, which means this is going to be 1 over 4 mu squared plus the variance of a, the expected value of a is 1 over mu, so the variance of it is going to be 1 over mu, the entire quantity squared. And so if I sum this up, let's see, it's going to be 1 over 4 mu squared plus this will be 4 over 4 mu squared. So at the end, we get 5 over 4 mu squared. Okay, so we've showed all parts A through D. These are pretty simple calculations once you understand the concept. Let's jump to problem number 4. Lifetime of the Simpsons dog, Santa's Little Helper, and cat Snowball are independent random variables with respective rates lambda d and lambda c. One of them has just died. Find the expected additional lifetime of the other pet. So this is a reference to Simpsons, the TV show. This is really the name of the dog, Santa's Little Helper, and the cat, I believe the name is Snowball. So one of these two pets has just died. We don't know which one, but one of them has died. We want to find the expected additional lifetime of the other pet. And we don't know which one has actually died. But we do want to know, we can still calculate, even though we don't know we don't know exactly which one died, we can still find the expected value of the additional lifetime of the remaining pet. Okay, so this is actually a pretty straightforward problem. I'm gonna just find out, D is gonna represent the dog, okay? and let D equal the lifetime of the dog. Lifetime of the dog, where it has a little helper, and let C equal the lifetime of the cat, Snowball. Okay, so I want to know the expected value, okay, of, and I'm going to say X is the lifetime. So additional, okay, of remaining pet. Okay, so we want to find the expected value of X. Okay, and we can condition then the value of X based on the first event, whichever has died. Okay, so kind of imagine starting from 0. This is my next event. Either the dog dies, the dog dies, okay, or the cat dies. It's one of those two outcomes. Then the second event must be, if the dog dies first, the second will be the cat dying. And if the cat died first, then it'll be the dog dying second, right? So we want to find this. This is X. Okay. So the expected value is going to condition on this first event. What happened first? So this will be the expected value of X given that D died first, okay, and the probability of D dying first, plus the expected value of X given the opposite case. C dies before the dog, cat dies before the dog, the probability of that event actually occurring. Okay, so let's start with the probability that the dog dies before the cat. That's simply lambda D over lambda D plus lambda C. That's the probability that the dog dies before the cat, because it's the minimum of two exponential functions between the dog and the cat. The expected lifetime then who's remaining? If the dog dies first, the person remaining, the animal that remains is the cat. So the expected lifetime of the cat right when the dog dies, simply 1 over lambda C, plus the probability that the cat dies first is going to be lambda C over lambda C plus lambda D. Okay, and right when the cat dies, the remaining pet is the dog. The additional lifetime for the dog right when the cat dies, that is simply 1 over lambda D. Okay, so that's our answer. It's a pretty straightforward problem if you understand the picture. Yeah, so let's move on then to the next problem, problem number 5. So problem number 5, this is a two-server system. The customer is served first by server 1, then by server 2, and then departs. So this is a system where everyone has to go through two servers. So you can kind of imagine there's server 1 here, server 2 there, and people arrive. They have to get service at server 1 first, then walk over to server 2, get service at server 2, and then leave. Okay. When you arrive, you find server 1 free and 2 servers at server 2. Customer A in service and customer B waiting line. So I'll put A over here to represent that A is in service. I'll put B over here representing the fact that B is waiting for service. And I'll put X as myself, or you, the person who just arrived. I'll represent as Y. Okay, so Y just arrives, and then we're going to go right into service because there's nobody at server 1. So as soon as I'm done at server 1, I'll walk right over, and then I'll wait for service at server 2. If both of those people are still there, or one person's still there. Otherwise, I'll go straight and get service at server 2 and leave the system. And so let's analyze the system. The first thing I want to find is PA. This is the probability that A is still in the system, still in service when you move over to server 2. Okay, so let's kind of look at how we're going to calculate that. So the only scenario in which A is still in service when I walk over to server 2 is right when I entered, I'm in server 1, A is server 2. I have to finish before A, right? As soon as I'm done with A, I finish in server 1 before A is done with server 2. I would simply then walk over, okay, and I would actually line up right behind B. And that's really the only case in which I will be waiting for A to finish at server 2. Okay, so kind of think of this as it's like saying the probability that you finish at server 1 before A finishes at server 2. So it's kind of like just a simple trying to get the minimum of 2 exponential distributions. So this is simply going to be mu1 over mu1 plus 2, because server 1 has to end before server 2. That's the answer for part A. Okay. Part B is a little bit more complicated. Part B states that it's the probability that B is still in the system when you move over to server 2. Okay, so you can actually break this down then into 2 parts here. And so I'm going to first erase, let me first erase part A, so we don't have a lot of space in this problem. Okay, let me erase part A. Okay. So in part B, I want to know the probability that I'm going to be waiting for B when I'm done with server 1 and walk over. Okay, sorry. Okay, so really there's only, I think, you can think of it as 2 cases, right? The first case is as before. I finish before A and then I walk right over. I'm gonna line up behind B, okay? Then this is a case that I will wait for B, right? Okay, because B is also gonna be waiting for A. So this is one case where I will actually be waiting for B. So the first case, okay, this is the probability that I finish before A, right? I finish before A, and that's already solved, right? We solved it previously. Slam mu1 over mu1 plus mu2. Okay. The second case, we'll think about it a little bit more. Okay. The second case could be A finishes first. Okay, so A leaves the system, and then B enters service. Okay, so B enters service. Okay, so B is getting a service server 2. But right after this happens, the next departure has to be me finishing at server 1, walking over, and then waiting for person B at server 2. That's the event where I'll be actually waiting for B. Okay, so the second case, you can kind of think of it as the probability as of I'm going to be less than A plus B. Okay, so if you add up the times for A plus B, okay, I'm going to be less than that. I'm going to be greater than A, okay, but I'm going to be less than B, right? So if you put A plus B together, so I'm going to be less than those two combined. Given that I finish after A, right? So that's the picture where A finished before me. A has already left, okay? After A leaves, the next thing to happen is for me to finish before B and walk right over, right? Okay. So you have to multiply this then by the probability of Y or me finishing before A actually happens. Okay. If I write out just this part over here, probability that I finish after A, then that would simply be mu2 over mu1 plus mu2. Okay, because the person at server 2 has finished before the person at server 1. So A, this is the probability that A finishes before me, Y. Okay. So given that happens, then what's the probability that I finish before B? Okay, that's simply mu1 over mu1 plus mu2, right? Okay. Another way of thinking about this is looking at the sequence of events. Okay, so this is time 0. The first event is, let's say, A finishing. Okay, if A, it's actually the first event, let's say I finish before everybody. Okay, then I'm going to be waiting for B for sure. Okay, so that's represented by the number 1 case. Okay, The other case is A finishes before me, Y, okay, and then the next event is Y finishing, okay, so or me finishing, okay. If those two things happen, then I'll be waiting for B, right? So this probability was mu2 over mu1 plus mu2, and this probability is mu1 over mu1 plus mu2. You have to multiply those two things because they have to happen in consecutive sequence, okay? So this is represented by number 2, right? So if I add up now the results together, probability that I wait for B is simply then mu1 over mu1 plus mu2 plus mu1 over mu1 plus mu2 times mu2 over mu1 plus mu2. And then you can simplify this if you want and to get a more better, a simpler looking answer. But also you could also leave it just like this as well. Okay, so that's the answer to part B. All right, so part C, I'm going to start with a clean slate here. I wrote down the results of part A and B. Now I'm going to solve for part C. So I want the expected time of T, where T is the time that you spend in the system when you enter, right? Total time. Okay. To make this problem simpler, I've given you a hint. Write the T as a sum of S1, S2, W, and WB. S1 is the service time at the respective servers. WA is the expected waiting time for person A to leave the system, and WB is the expected time that you wait for server B, or customer B to get service and leave the system. Okay, so ultimately, I'm solving for the expected value of T. Then I can rewrite this as the expected value of S1 plus S2 plus WA plus WB. Okay, I think right away you can tell what the expected value of S1, the expected value of S2 are. That's simply asking for the expected service times at those respective servers. And those are pretty straightforward, right? This is simply 1 over mu1, and this will be 1 over mu2. Yes, those aren't very interesting. What we would have to figure out then is the expected value of WA. Okay, how long do I wait for WA to finish and leave, right? Okay, so if you look at the picture again, the picture is A is already in the system, already getting served at server 2, and this has a mu2 distribution, okay? And then B is waiting for A, and then I just entered the system, and I began service at server 1, and that's me right there, right? So that's Y or U, okay? So you're at server 1, okay, and person A is in server 2, and person B is waiting for service at server 2. So how long do I wait for A? Whatever waiting I do for A, it's in respect to server 2, right? So for example, let's say I finish before A and I walk over and I get behind line of B, okay? Right at the instant, the expected time for A to finish at that server will be 1 over mu2. So this is the amount of waiting I do for A because A will be getting service to server 2, right? So that it's the same logic here. That you just simply apply that logic. So I can rewrite this as expected value of the service time of A, okay, given that A is still in system, okay, and the probability of this portion happening, I'll call this A, and that's PA. So this is not by coincidence, this is by design. We got this from part A, right? We already have that from part A, okay, so this is going to be something times what we got in part A, which is mu1 over mu1 plus mu2. Okay. So if A is still in the system when you walk over, you have to wait for that person A. It's simply the service time to server 2. So this will be 1 over mu2. Okay, so the expected value of WA, then it's just the product of these two terms. Okay, the same logic applies for the waiting time for person B. Okay, it's the expected service time for B. Okay, B is still in system. Okay, and the probability of B. Okay, and again, this part we got from part B, right? And if we plug this in then, so in this picture, if you're waiting behind B while A is getting served, that waiting time is already accounted for by WA, right? So really the picture you're talking about is when A is already left, okay, and B's getting served at server 2, and you're waiting for server 2. Okay, the expected time you expect B to spend in that server is 1 over mu2. So this is, again, just simply becomes 1 over mu2 times what we found in part 2, which is mu1 over mu1 plus mu2 plus mu1 plus mu2 multiplied by mu2 mu1 plus mu2, the whole quantity multiplied, right? Okay, so then you're going to put expected value of t, then simply you're going to put everything together. I'm not going to write this all out, but you have to use pieces, right? It's going to be, let me change the color so you can see. It's going to be this portion. So you're going to add those two portions, okay? And then this will be the third term you're going to add. And the last one you're going to get, it's going to be this big term right here. Okay, so you're going to add all of that in. It does simplify something nicer, but you can just kind of write it all out. But those 4 terms are what you're going to need. Okay, so you sum all that up, and that's your final answer. Okay, so a little bit more challenging, but if you break it down this way, it's actually a much manageable problem. Okay, so now let's move on to problem number 6. Certain scientific theory supposes that mistakes in cell division occur according to a Poisson process with rate 2.5 per year, and that an individual dies when 196 such mistakes have occurred. Assuming this theory, find the following: the mean lifetime of an individual. So this theory assumes that your life is basically defined by, when your body makes 196 mistake, and that's when you die. Right? So if you start from 0, okay, your body will make the first mistake at some time from birth, right? That's the first mistake, and then you make the second mistake, and then third, fourth, and on. Ultimately, your last mistake is 196 mistakes. Okay? Because this is a Poisson process, we know then that the expected time until that first mistake simply 1 over the lambda value here, which is going to be 2.5 per year. Okay, the expected time from the first to the second mistake is again 1 over lambda. Okay, so if I want to find part A, I'll call it t. This is the total time. So x1 is the time until the first mistake. x2 is the time between the first and the second mistake. So you can call these x1, x2, x3, etc. Okay, so until your 196 mistake, okay, that's the total time until you make that, your body makes that 196th mistake. Okay, so then if I want to find the expected value of t, simply the expected value of x1 plus x2 all the way to x196. And I can break down even further. Expected value of x1 plus expected value of x2 plus the expected value of x196. Each one of these are just 1 over lambda. So 1 over lambda plus 1 over lambda, 1 over lambda. There's 196 of these, so it's 196 over lambda. Okay, lambda here is given 2.5 per year. Okay, so then the expected value of t is simply going to be 196 divided by 2.5, which turns out to be roughly 78.4 years. So the expected lifetime in this scenario is 78.4 years. Okay. Part B, I wanted the variance. So it's the variance of t, okay, which means I'm finding the variance of x1 plus x2 all the way to x196. So kind of did a similar problem earlier in the homework set. Okay, you can break this up. If you have a variance of the sum of independent random variables, I can split these up and say it's just variance of x1 plus a variance of x2 all the way to the variance of the 196th
mistake, right? So then that becomes 1 over lambda squared plus 1 over lambda squared all the way, and it's going to be the 196 one.
Okay, so put all that together. This is going to be, there's a 196 divided by lambda squared, or 196 divided by 2.5, the whole quantity squared, and you're going to get roughly 31.36. Okay, so that's the variance of the total time it takes for your body to make that 196 mistake. Okay, so now let's do part C. So I'm gonna make a little bit of space for myself. Okay, so I'm gonna write down the answer for part A up here. It was 78.4 years. Okay, and then for part C, it was 31.36. So then I'm gonna delete all of this. Okay, pause it really quick. Okay, resuming here, I erased everything off. I want to find now part C. Approximate the probability that that an individual dies before the age of 67.2. So this question really tries to relate back to what you should have already learned and applied a few times throughout your your career, your curriculum, your academic career. You've all taken ISY 330, Providence Stance, and you've taken SPC and all these other classes where you may have probably already seen this. The basic idea is when you have a random variable that's a sum of other random variables, when you put those all together, oftentimes it's going to resemble a normal distribution. So it's really the central limit theorem in action. Okay, so if you were to look at the variable x1, x2, and x3, so remember we were trying to find the expected value of t, which was the expected value of x1 plus x2 and on, right, all the way to x196. Each one of these xi's are exponential distributive parameter lambda. Okay, but if you look at t though, t is actually going to have a normal distribution with a mu and a sigma squared. Okay, so that's the central limit theorem. Essentially, that captures the central limit theorem. Okay, if you look at the summation of these exponential variables together, it's going to resemble a normal distribution. Okay, so if we know that, then we could actually, this is a pretty simple problem to solve that. I want to know the probability that the person dies before the age of 67.2. So that's like asking, what's the probability that this t variable is less than or equal to 67.2? Okay, and we know the t value is going to have a normal distribution, right? So normal distribution, and the mean we got from part A, which is 78.4, and do we know the sigma? Yeah, we do. We got the variance, right? So you just square root to get the standard deviation to see what the spread looks like, right? So so basically, when we're trying to find the probability of the lifetime being under 7.2 years, it's like asking, the probability. What's the probability of my z value being less than? Okay, so I got to transfer this 67.2 into a z value. So z is going to be 67.2 minus my mean 78.4 divided by my standard deviation, which is the square root of 31.36. Okay, you can calculate this on your own. There'll be some z value. Okay, so then I'm going to call this. Actually, I'll write the whole thing out over here. 67.2 minus 78.4 divided by the square root of 31.36. If you solve this out and look at the normal distribution table and see where this falls, you're going to get roughly 0.02277. Okay, so graphically, what does that mean? You're probably somewhere out way over here, right? You're probably like somewhere over here. Okay, this is probably 67.2, somewhere out there, right? So the probability that you die before 67.2, it's a very small probability, assuming this mean and standard deviation. Okay, so that's it. Homework number 3. Hopefully this was a good problem set to look at. I think this is a solid set. I think you can learn a lot from this homework set if you actually try to understand it, rather than just trying to, get the solutions or try to just work with your friend. You can always help each other out, but you really have to try to understand this. I think this is a very good preparation for exam, and also it's really just a very honest check to yourself. Do I conceptually understand all of this, right? So, I mean, you have other questions on Blackboard, representative exam questions, but I think this homework set is, again, a good reflection of how well do you understand these concepts. Okay, so that's homework number 3. I spent some time to go over this with you, even though I've posted the solutions already. Hopefully this is helpful for some of you. If you have any questions, make sure you contact me. And best of luck on your preparation, and have a great weekend. Take care.